Hello, ladies and gentlemen. Today we're going to start off with terminology, and we're going to start off with what we mean by terminology and explain a couple things. So we got all these letters, and Q is equivalent to heat. The delta E, the change of E, is internal energy, where E is internal energy. H is enthalpy, S is entropy, and G is Gibbs free energy. We're going to get to that later. We're going to focus on heat, work, and so forth. And I want to point out is that heat and work is not capitalized, but everything else is. And so when we're looking at things and we start talking about all these variables and what they mean and actually how to define these things, we got to realize one thing is that the capital letters mean something. If that variable is capitalized, this is what we call a state function. And when we chemists talk about state functions, and this can get a little bit misleading, it's simple. The state function means that the variable is independent of the path taken. So if we have a temperature and we do a couple things, and the temperature increases or decreases, temperature is a state function. So is pressure and volume. It's all independent of how we got there. However, heat and work is not independent. It's actually dependent on what we do to the system. So we got to realize is that there's hidden meaning in the capitalizations and in these terms that we're working with. We are getting, I want to say, detailed, very sophisticated with how we explain things. And this, what gets hard for a lot of students, is that the subtlety of our terminology, of the variables, can get lost. And you guys need to realize that variability. Realize that subtlety in the variables so you understand what's going on. So let's go on, let's talk about heat. Heat is basically the flow of energy from one object to another. And this is all what this unit is doing. It's looking at heat, how heat flows. And in addition to heat, there is work. Now, heat is energy, flowing from one to the other. Work is the action performed by energy. And is work done by the system, where it's negative work, or it's on the system, which is positive work. So we have those two relationships happening at the same time. Now, if we go and do some W work and heat together, we're going to call this a term in the change in internal energy. And again, now we have a state function. Internal energy, the amount of energy inside the system. And we could look at the chemicals. And when we talk about a system, for us, sorry, no, I've been touching my pen. Come on, system is the chemical reaction. Now, when we look at, say, O2 plus 2H2 forms 2H2O, it's not two blocks, it's all these molecules in a gas container forming water. And that's our system. Now, there's other things in the system. There's the volume. It's what, they may be, if we take lead nitrate plus 2 potassium chlorides to form PbCl2, which is a solid. This is our system. Now, both of these are in water. But the system is all these molecules reacting together without the water. And this can be hard for students to understand, is what do we mean by the system? The water is not going to change energy. It may, well, I should say the water itself is not going to donate energy to the system, but it is the environment that when something happens, it's going to be affected by the reaction. It's either going to absorb energy or give energy to the system so it can react. And it's a little bit more, this is what we call the subtlety of all these reactions. You got to get your mind around it. And a lot of times, I have a tendency to kind of ignore some of the subtleties to try and get the point across. The reaction of lead nitrate plus potassium chloride gives me lead chloride that precipitates out. We don't care about the water. We're going to have some type of energy being released, but it's so small it doesn't really count. And where's it going? Where's it coming from? So be aware of that. It's subtlety. This is the fun part about chemistry. This is, what's going on. So let's take a look at the definition of work. In chemistry, it's defined as a change in pressure times volume. This is what we call gas when we look at gas systems. And remember when we talked about gases, pressure and volume changed. nRT is held constant. Number of moles, R is constant, T is constant. So when we're looking at work, if we kept all those things, if work is done on system or by the system, we should see a change in pressure or volume. So we either get one of these two, which means it could be either one of these two. Change in pressure times volume, or the pressure times the change in volume. So change in pressure times volume, or pressure times the change in volume. So be important. This is where a lot of chemists forget. And the reason why we pick this to define work, because work is defined as force times distance traveled. Out of these two options, change in volume means something is being expanded or contracted. Something's moving. Here, nothing's moving. If nothing's moving, no work has been done. So we're going to use this equation, P times change in volume, to define work and help us with work. Now we're going to talk about moving on to another variable, and that's enthalpy. Enthalpy is defined as the change in internal energy plus the work. And sometimes, remember, heat, this is also can be equivalent to Q. So the change in internal energy plus the work being done gives us enthalpy. But in order for this to be true, we have to do it under constant pressure. Has to be done under constant pressure. If pressure is not constant, and we do work, we can't find enthalpy. And this is key. We're looking for the actual state function of heat, enthalpy. So we're looking at the change in volume, work being done on the system. Now, and I'm going to say this is under Q with constant pressure. But guess what? If we held volume constant, work is 0, now we're looking at the change in internal energy. Again, this is going to be important. So we're looking at two different state functions, meaning the heat flow. One we call a change in internal energy, which is hard to measure because we got to keep the volume constant, and that's actually harder to do in our level of chemistry. But we can keep things under constant pressure so we usually look at delta H, the enthalpy of a reaction. Now so we're going to talk about Gibbs free energy, entropy a little later on, and I'm going to hit those again later. But this should help you with this first tutorial. So we've been giving you all these subscripts. All these letters, all these variables are going to have subscripts. And what do they mean? And it tells you what type of physical chemical process we're trying to measure. And that's important because this is where the subtlety comes in. This is a lot of subtlety. It's not complicated. Don't make this too hard on yourself. Just understand what we're looking at. So this is what all these subscripts mean. R is reaction, or you may see it as RXN. Both of those are chemical properties. It has the heat of reaction, internal energy of reaction, heat of the heat of action. So these two are chemical. Come on. This is the physical property of vaporization, going from a liquid to a gas. And remember, L is equal to liquid G is equal to gas. Make sure you know these letters as well. S is a solid. This also means the system. Look at our system, this reaction. What is happening? Fusion, this is our going from solid to a liquid. Not only, so if we're going from a gas to a liquid, the heat of vaporization is actually negative. And same thing here with the fusion. The opposite is we just change the sign. Formation. How do we form something? Taking from the basic elements. So formation is, say, Cl2 plus lead goes to PbCl2. This is what we call the heat of formation. So with this reaction, we take these are the delta H is 0, and then we figure out what the change is this in. And we'll talk about that with Hess's law in the next lecture. All right, hope this is understandable, guys. Have a nice day, and let me know if you have any questions.